Yeah.
Okay.
Okay.
All right. So be sure to be back here by 10:15.
Yeah.
Hopefully this works better than when I used my Zoom account, and it's clearer. It looks better to me on the screen.
Hey, you're upside down.
Oh, no. Just a second. Hi. It's upside down.
No. Upside down?
Yes, the printing's upside down.
Where's the video? Okay. Video settings. Oh. Yeah. Video. Yeah.
You stay here for 5 minutes.
Okay.
And you'll leave again.
Yeah.
Okay. So we want to get beam deflections. Sometimes we want to get them just because we want to know how much stuff deflects. Quite often we need to get deflections to solve statically indeterminate problems. Very common. We're going to focus on using the second order ordinary differential equation, because one of the things we're always going to want is M, this bending moment, because that's the principal thing that leads to bending stresses. Okay? And bending stresses, as I've shown you, are much bigger than the shear stresses in the center of the beam. So the approach here has got 3 steps. You do your statics, free body diagram with the entire structure. In complicated structures, you may have multiple free body diagrams. And you get M. You get M for different x's, where x is the longitudinal length along the beam. Okay. At the end of this exercise, you'll know if it's statically indeterminate or not. Most of this analysis is 2D. There are 3 equations of statics in 2D. Some of the force in the x direction or horizontal direction, some of the forces in the vertical direction, and a moment. Okay? You can exchange these for 2 moments and 1 force, but you, in terms of making this decision, you want to think of 2 forces in a moment. That's all. Okay. Oftentimes, the force in the x direction is non-existent, so satisfaction of that condition is automatic. So you end up with 2 conditions. Then if you have 3 unknowns, it's statically indeterminate. If you have 5 unknowns, it's not only statically indeterminate with 1 unknown, it's got 3 extra unknowns. Okay. So you want to make that decision. That feeds into what you do next. You're going to write down your ODEs like this, and each of these will require 2 end conditions. Then you have to have extra end conditions to recover these statically indeterminate terms. So you're going to know the sum of the end conditions, and there's no point in proceeding until you've got a well-posed problem. A well-posed problem is the number of end conditions equals the number of constants of integration plus the number of statically indeterminate variables. Some people start solving the problem, then go along and then put the end conditions as they're going. It's much better to think it through at the outset. Okay? Occasionally, you'll have extra end conditions, and that'll mean there's some redundancy, that if you solve one set, some of these other end conditions will be taken care of automatically. What you can't have is inconsistent end conditions. That's not a well-posed problem. You can't solve it. And if you have it lacking some end conditions, then it's not unique. Okay? And then you proceed to solve. And check. And with this approach, you can do a complete check. You can take your final answer, put it back into the differential equations and the end conditions and make sure it satisfies. There are, the book does some graphical solutions. In practice, you're going to find some engineers like graphical answers, other people like formulas. It'll be a matter of what the preference is at the place you work, okay? But once you get these formulas, you can certainly do this check relatively easily. You can always check things by doing them twice. Okay, that's not a bad thing to do, but it is quite possible to make the same mistake twice. I can speak from personal experience. When you have an independent check, like by substituting these back, then you catch that, or you tend to. Let me make some comments. Okay. You can go. Let me make some comments on the homework you just passed in. This problem here. This could be a real problem, okay? I don't know where they got this from the book, but you get shafts and you have different loads. The location of the loads is a little bit funny. Normally the loads would be in from the ends a little bit, okay? Well, I'll post this solution. But this is just applying what I just said. So here's the statics, here's the given forces, here's the end forces, and you can solve. You have 2 equations in effect because there are no forces laterally, okay? And so I took moments and some forces, and you can get reactions. And then once you've got the reactions, you can go get the moments. Now this force here was in kilonewtons. So if X is in millimeters, at this point, you're getting M in Newton meters. When you start to set up your ODEs, you better switch all to Newton meters. And so you put X in meters, then you change your forces to kilonewtons. So what's going to happen here, otherwise, once you start to integrate, you'll get inconsistent units. What's going to happen here is this went to 10 to the 3 because it went back to newtons, and now X is in meters. You can look at this stuff at your leisure. EI is varying, okay? We had an end condition simply supported. We have matching conditions for the deflection itself and the slope, okay? Here's another different EI, the last governing differential equation, and we have matching conditions, and then we have a simply support condition. So in these 3 differential equations, 1, 3, and 5, we have 3 second-order differential equations. The problem is statically determinate, so we need 6 end conditions. We have 1, 2, 3, 4, 5, 6. So it's a well-posed problem. The analysis is really straightforward. You just integrate and apply the conditions. I've worked this to 3 decimal places. I plan to give the answer to 2 decimal places. I'm working an extra decimal place. You solve the system. Here are the answers to 3 decimal places. And then when I put it all together, I just use them. For example, this minus 11.639 is minus 11.64. I multiplied by 1,000 so that the delta will come out in millimeters. These deltas are going to be very small. They're a fraction of the diameter. Okay. Actually, I think maybe the biggest one's about 0.1 millimeters. So you could even multiply by another 10.3 and have these answers in microns, which actually would be preferable use of the SI system. So there'd be a 10 to the 3 on top of each of these. Okay. And then I could check. I went back and put these in the end conditions and all the end conditions and the ODEs, and they met them. Okay. This tedious. Okay. I'd appreciate it if anybody, I'm not saying this is 100% correct. I hope it is. It could have a little round off, but I suspect it is. But if anybody finds any errors in this, please let me know. For that matter, if you find any errors in any of the work solutions, please let me know. But what I think is going to happen if you do a lot of this stuff is you'll run into a code. Okay, you're going to be able to do one of these problems yourself. For that matter, you could use this problem, okay, and run it and see if you got the same answers, just to make sure that you're communicating with the code appropriately. And that may not be your fault. Sometimes the instructions for these codes leave a bit to be desired. They rely on people actually knowing you do X and without you being told to do X. And that's not uncommon. So it's a lengthy exercise. If you manage to get these sort of solutions, you did very well. But it is somewhat tedious, without a doubt. It is somewhat tedious doing this stuff. Let me make a comment on this simply supported case. On superposition. I did this problem with superposition. What superposition lets you do is it gets this unknown M naught very quickly. We got that in a couple of lines, okay? The length of solving the problem with superposition, getting the displacements, is very similar to the length of this solution. The difference is here when you approach it by doing integration and not using superposition, it's not towards the end that you get what the unknown moment is. So superposition will get you statically indeterminate reactions relatively quickly. That's where it's really great. For actually getting the total displacement and solving the whole problem, if that's what you want, it adds a little bit, okay? But not much. But it gets this answer in about 2 lines, okay? There are far more extensive sets of tables of cantilever beam and simply supported beam deflections than in your machine design book. And so if you end up doing quite a bit of this, you want to use that. And superposition means you're using somebody else's work, means you're doing less work. And so it becomes less tedious than what I just did. However, for some things like the step shaft, you've got very little choice but to go through and do the analysis yourself. Let me make a couple of comments on those lines about example 17. Any questions on that? Okay. This was a step shaft. And it had one force here, I believe. And another force right in the middle. When you get problems with 2 forces, quite often it's advantageous to separate, divide and conquer. So just do F. Well, the nice thing about F, and this happens not infrequently, have a central load, is it's symmetric. I haven't put in the lengths. They're in the problem statement. I think this was little L, and this was big L. But this is the line of symmetry. So since it's symmetric, you have differential equation here. Let me put this length. You have one differential equation for there. And then I think this total length was L. So this little length here is L upon 2. And any symmetric problem, you only have to solve half of it, okay? So you've just got 2, whereas here, when we did this thing, we had 1, 2, 3, 4. Now we just got 2, so it's quite a bit simpler. And you want, the conditions are going to be the simply supported condition, the matching conditions, okay? And the last condition here is when this deflects symmetrically, it looks like this. So deflection on this side is equal to this. So there must be 0 slope here. If there was a slope here, then the deflection on this side would be different from that. And so the symmetry condition is that's at the end point. So this is a relatively simple problem to solve. And it isn't just a freak of this particular problem. It is quite common to have a central load and sharp. Let me show you something that might help you with the P contribution. When you get to the end, P and you P, you're going to have ranges. The L, you're going to go from here to here because this has got a different diameter. Then you'll have this range here. And when you're doing the bending moment here, if you do it from the end, then like this, here you have RB, which we solved for using statics. As far as P was concerned, what's that? This distance is X. Then we put in the shear force and the bending moment in the positive direction. Shear force is positive, it reduces the clockwise rotation, so that goes in that direction. And M compresses the top of the beam. Then we take moments about here, and we get M is RB times this distance, which is L minus X. The following approach to solving the differential equation will help you. If you have D2 delta, I'm going to change the sign on this.
Dr. Sinclair, would that L be the lowercase l above?
Oh, sorry, that L, this L, I misspoke. Yes, thank you very much. this L is the total length. So L plus, okay?
Okay.
L plus is the total length. So it's L plus 2L, okay? Thank you, okay? Very good. So when you take these moments coming in from the other end, the moment or the distance here is going to be the total length minus the x, okay? When you integrate this, I'm just going to integrate this and call it x minus L plus squared upon 2 plus a constant of integration c. This is certainly correct. If you differentiate this, you get 2 comes down, it cancels this 2, and you get x minus L plus. Okay? But here's the power. If I integrate again, now it's just like, call this thing z if you like. This is z squared, so the integral of z squared is z cubed divided by 3, well, z is in fact x minus L plus cubed divided by 3. 3 times 2 is 6. But I do the same thing with the c. And if you differentiate this, you'll get this, okay? The advantage of this is that delta equals naught at x equals L plus. You just got rid of one constant. Okay? So by separating these, this is a simpler problem. Even the p problem has 1, 2, 3 regions, and the constant here, the constant integration goes to 0. I've got this constant equal to 0. So I've got 2 matching conditions here and here, okay? So I've got 4 constants and 4 end conditions. Whereas this problem, when we did it, had a gross number of something like 8, and we got rid of 1, so we had 7 and 7. So this is a lot simpler when you do this. Okay? Are there any questions on that?
So what did you actually do?
What did I'm
Like
solving.
you separated, you said you separated the forces?
Yes. So this problem here is equal to the problem with F and the problem with P, and I separated the two. So yeah, let me make that clearer. So I said this is equal to, I'm just going to sketch the beam as a straight line, that plus that. Okay. And by doing them separately, they become easier problems. Okay. The first one's symmetric, and as I said, that happens quite often. You only have to do half of it, so that makes it simpler. But even the P problem is simpler. Even the P problem, you now have 1, 2, 3 regions instead of 1, 2, 3, 4. Okay? And then if you use this little, I'm not sure I'd call it a trick, but if you use this approach here, okay, then you can get rid of one of these constants very easily. So if you end up doing a lot of these problems, this approach will help you get the right answers. Okay. So any other questions? Is that okay? Can you see how I separated the two?
Yes, thank you.
Okay. So you don't have to do it. And when I did in class, I put them both in. And you could have done that for the problem I just solved in detail in problem set 4. I don't think it buys you that much there. Okay. This one here, particularly simplified because of the symmetry for the F. All right, well, let's move on to a different topic. It still deals with deflections. Buckling. There's a significant discussion of this in your book, Juvenile and Marshall. And we'll cover most of what's there. Okay. But, what is buckling? it's large deflections caused by compressive load. Okay. So here, hopefully you can see this. Okay, now I've got it lined up so you can see it straight. There's a little bit of an angle here. I'm going to push on this ruler, and eventually you see you get large deflection. What does large deflection mean? It means the deflection is several times the thickness. You know, in that step shaft problem I did, the deflection were, 10% or less of the thickness, less than 10%, maybe 1%. Okay, but here the deflection is a multiple of the thickness. That's what's large. Okay, so the situations like this, what I just did with the ruler, the ends were free to rotate in my hand, so that it's like it's simply supported. I supplied an equal and opposite force F, and I got a deflected shape like this. When this delta was a multiple of the thickness, significant multiple of the thickness. I don't know if you can see. There we go. That deflection looks to me like an inch. The thickness is the 16th of this ruler, so it's 16 times. So these are large deflections. Well, these large deflections can make the device fail to work. The most common thing is they jam. It doesn't spring back. Okay? That's not actually the principle. This happens. But what happens is buckling can lead to large bending stresses. Which in turn can lead to yielding or even collapse. If you want to do a demo of this, if you get a Coke can and empty it and you step on it very, very carefully, then that's a very thin aluminum structure. If you step on it very carefully, it'll take your weight. I'm not sure it'll take everybody's weight in this class, but certainly I've done it and it'll take my weight, and it's about 180 pounds. If you then reach down and touch the sides and promote buckling, they'll start to buckle, the thing will collapse and the can will be crushed. Okay, that's a simple demonstration of this sort of phenomenon. Once these things start moving here, in this case here, you just have an axial stress. The axial compressive stress is the force divided by the area. Here you start to get a bending moment when you're out here, maximum bending moment, F times delta, and then you divide by the section modulus. And if this thing is thin, that section modulus can increase that number significantly, and you get a large stress. Now, that's not to say these things always have to collapse. I mean, we just did the ruler, and okay. If I kept going far enough, I could probably break this ruler. Okay, it's plastic, so it's going to break in a brittle fashion, not yield, but it's not breaking, and then it goes back. So this can happen. I don't want you to think that when you get buckling, you necessarily have things break. It's just the propensity to do so is higher. So what we want to do is we want to figure out what load causes this. And if we can figure out the load that causes this, then we can design structures or components so they stay below that load and they don't buckle. So what we want to do is we want to determine this thing we're going to call FC. The book uses PCR, they're the same thing. This is, I think with my handwriting, this will be clearer, that's all. This is the C stands for critical or compressive load that just starts at the buckle. Okay, when I pushed on this thing here, so you could see it, I went past that load. That's just starting to buckle. Okay, that's what the critical. I went further still, so you could see bigger deflection, but when it just starts, that's what FC is. Okay? If we have that, then we can design to avoid. We can change our components so that it doesn't happen. Well, the longer this beam that's under compression gets, the easier it is to buckle. Okay. What I'm saying is, this is a very funny looking thing to buckle. And it buckles very easily that way. But if I put it this way, I can feel it's a little more force, and you can do any of these demos you should be able to do yourself. But if you want a more graphic example, this is a beam this way because its length is relatively big compared to its thickness, and I managed to buckle it. If I was to turn it like this, oh, well, you can't see. If I was to turn it crossways like this, I can push like this very, very hard, and I will not buckle it. So you would expect then that F is proportional to 1 upon L. If you make things bigger, length longer, then they're going to get easier to buckle. You can try this if you have a block of paper here. You can try this yourself, like taking this length here and then this length this way, and you'll notice in your hands that the shorter one is harder. You can also expect F to be proportional to the bending stiffness. EI is the bending stiffness. Okay. Depends upon the cross-section properties and the modulus of the material making it. And the stiffer it is, the harder it is. Okay. Well, given those two, let's look at the units. So we combine these. We want to make them dimensionally consistent. So the units for EI, E is force over length squared, and I is length of the force, fourth. So this is F, L squared. So that would imply then that F is proportional to EI over L squared. That'll get rid of the L squared, and this will just be a fourth. So we can expect that the buckling load is lambda EI L squared, where lambda is a constant of proportionality. It's a dimensionless constant. Just a number. Well, let me do an example and see if we can find out what lambda is. If we know this, then we'll have some strategies for making this bigger. We've got a certain compressive force in a design, then we can make I bigger, or we can reduce L, okay? If we reduce L, that'll make this go up. If we make the diameter, say, double, then you'll get a factor of 16 in the stiffness here. Or we could pick a different material, that's less common. But we need to know what this lambda is to make sure we're getting the right values. So let me go and get what FC is for a simply supported beam, just like the ruler I demonstrated. I can do this for either a beam or a column. When it's a beam, it's horizontal. We draw these little things. This is a pin joint here. There's a pin joint here. When I held the ruler in my hand and compressed it, there was no resistance against rotation at the ends, and indeed it did rotate at the ends. Okay, that's what this means. It doesn't mean you have the pins, but in effect, the thing is free to rotate at the ends. And this is a beam. It's horizontal. If we make the configuration vertical, we have a column.
No, Dr. Sinclair,
Yes.
how will you know if when you compress these beams, they're gonna buckle or bend, like in materials lab, when we did compression on those steel rods, they would crinkle up or like increase in diameter?
Okay, well, I don't know exactly what you did in the materials lab, but we knew if they didn't buckle, they were probably fairly fat, okay? And that means that I would have been big, okay? So because the diameter was big. We'll talk about a ratio of diameter to length and try to understand. In that case, if you took them in the elastic region, you'd hardly see any deflections. But once you started to yield, then they'd squash. And yielding in the plastic flow, the material essentially flows incompressibly. So if you shorten it, then it's going to get wider. Okay, it may not do that right where the grips are, because it may be crimped there, but elsewhere it will. Okay. And that's a competing mechanism with buckling, when you can have yielding, which occurs for short, stubby columns. This is a column, it's vertical. But when it gets skinny, then it will buckle. Okay. And so for this ruler, which I buckled, it's a foot long. Okay. So it's lengthy. If I just took, I tried to do this, but I couldn't show it to you, just the width of it, then I can't buckle it. And if I put enough load there, this thing would just break. Okay. So you have two competing mechanisms. For metals, which yield, the competing mechanism yielding and buckling. And depending on the relative length, you'll get one or the other, and we'll deal with that. Okay, so they're both, and that's a decision we'll have to make which one we're going to get. So we'll do that. But in the short term, we'll just try and figure out buckling, and later on we'll come back and think about yielding. In structures, in civil engineering structures, the walls have columns in them. Now, occasionally, if you have some state-looking mansion, it may have columns outside. You can see the columns, but inside the walls in my office, there are vertical members that are under a vertical load. So there's columns throughout the structure, and these are often loaded in compression. Beams less likely, but in mechanical engineering, we have plenty of things like connecting rods and stuff like that, which will act like beams and they compress. Civil engineering, this is the dominant form. So what we want to do is we want to get rid of FC. And that's tantamount to finding lambda for this configuration. To do this, let me do a free body diagram in the deformed position. X is going to be my coordinate up to some point here. I'll blow up this diagram a little bit. When it's deflected, in the buckled position, not this position, but after it's buckled, it would look like this. I've expanded this part here. And now it's buckled, so it has some deflection delta. I put the force F for both of these, so the reaction here is F. There's no moment here. If I resolve vertically, well, let me put the arrow in there, it'll be clearer. If I resolve vertically, I'll have an equal opposite force here, F, but I'll have a bending moment. Let me call this point 0. If I sum the moments about 0 and make that require to be 0, then I'll have M, which is counterclockwise, plus F times delta, which is also counterclockwise, equals 0. If you like, then M is minus F delta. So that's doing the statics. Let's set up my differential equation. M over EI this is a second order ordinary differential equation, simply supported. So we're going to have that delta equals 0 we could rearrange this. I'll put this delta term on the other side. And this is one of the standard ordinary differential equations you get in ME. I think you may have seen this, but let me show you. We'll come back and solve this. You won't solve that many differential equations in ME, but this is one.
Could you scoot the other paper down, please?
Sorry?
Could you scoot the other paper down, please?
This one? Oh, yes. Sorry. Yes.
Thank you.
Thank you. The normal way you get this equation like this is in vibrations. You get something like this: the second derivative of the deflection with respect to time plus omega squared with the frequency times y equals 0. That's free vibration. And the solution and you probably saw something like this in your calculus class. You may not remember it, but here A and B are constants. And this satisfies that equation. You can prove that very quickly by differentiating, sticking it back in. Y dot differentiating once. If I differentiate sine omega t with respect to t, I get an omega. And the differential of sine is cos. If I differentiate cos, again, I get an omega. But the differential of cos is minus sine. Now, if I differentiate again, I'll get another omega. Now I'm differentiating cos, so I get a minus sign. And I differentiate this, I get another omega. And the sign goes to cos. Well, A sine omega t plus B cos omega t is just y. So y double dot plus omega squared y equals 0. That's the differential equation. So this is the solution. I hope I didn't waste too much of your time doing that. But what you've got here then is delta equals y, x equals t, and this thing here so using the standard solution, the solution to this equation then, the general solution, usually called general solution because you haven't adjusted the constants yet. It's going to be delta A sine omega t, omega x, omega is the square root plus B cos. So that's the general solution to this. Now we have to apply these end conditions. You could do just exactly what I did. You could differentiate this twice and stick it back in here, and it would satisfy this equation. So now if I apply the end conditions, delta equals naught, that equals naught. Let's call this 1. We've done 1. So if I put x equals naught, this will be fine. Sine of 0 is 0. This will not. This will give me B. So get B equals naught. I also have it equal to 0 at L. So I'm going to have at L, and that's going to be 0. Okay. Well, one answer to that is A equals naught. And that's certainly the correct answer. That's just no buckling. But an alternative answer is if this whole thing here is equal to pi. Or if you like, F upon EI is pi upon L. So now back to my solution then, what does delta look like? I can substitute for F upon EI, the square root thereof. It's going to be A sine, well, this square root was pi upon L, so pi x upon L. So what does this look like? Here's the beam in its original position. If we go from X to L, it looks like this. And when X equals L upon 2, this will be sine of pi upon 2. So the middle part here, this deflection is A. Well, when does this happen? Well, it happens when this holds, and that must give us the critical buckling load. So when this holds, if I square both sides of this, I get this must be the critical load. So FC so that's what we wanted to find. This means that the constant of proportionality was pi squared. That's what lambda was, about 10. Okay. So we got the same dependency on the bending stiffness and inverse dependency on the length squared as we had anticipated from this analysis. But we also got the coefficient of this here. Well, are there any questions on that? Okay, well, I'll do it. We'll have a break for 5 minutes and I'll do an example and see how well this little thing works. Okay. All right, let's break for 5 minutes. Okay. I'm going to do an example. I've got a ruler, and we'll see how well this works. This is the first mode of buckling. And it looks like this. Now, if I go back to this equation, there are other ways I could satisfy this. I could have well, we just did the case when this is equal to pi, but there are lots of roots for sine. There's 2 pi, 3 pi, and so on. These are higher order modes. This one's called the second mode, and so on. So what I'd get for this one is I'd have that um, and so that force is 4 times this force here. So normally you don't get to this, right? If you're applying the force, you see this first, and you get back on the first mode. You don't get to this. Okay. However, let me show you what the mode looks like. Delta is a sine the square root I substitute for that 2 pi upon L. And this looks like this. This is the height L. When x equals L upon 2, it's also 0. So it looks like this. While, as I pointed out, if you're just loading this simply supported beam, you're going to hit this load first, so it's going to buckle with that first mode shape. Okay. And you won't see this. You can come in and hold the middle and force it into the second mode, and that'll get you a higher buckling load, so that'll inhibit the buckling load. This is a common technique for reducing buckling. If you have this beam or column, it's vertical, so it should be a column, and it's got hinged ends here, if you come in and put a support, a pin support in the middle, then your buckling load will go up by a factor of 4. Okay? So you can use this as a way of trying to beat buckling. This is a common practice. If you see something buckle, work up to the middle of it and clamp it there, and you'll probably stop the buckling. Well, let me check. Yep.
Mathematically speaking, that's the same as reducing the length of the beam by half.
Yes.
You're just adding.
Yes. Yes. So I wouldn't even say it's mathematical. I think that's physically insightful of you. Okay. It's like you had 2 little beams of length. Okay. And you reduce them by half, so that put the load up. Okay. And that put it up by a factor of 4 exactly. Okay. That's what you did. And so I've done this in consulting cases when people have large vibration noises and they didn't like it, the thing wobbling backwards and forwards. You go up and you put, you clamp the middle of it, even just with your hand, and you change the frequency by a factor of 4. And so the noise will be probably out of the audible range. So this is a standard trick in engineering to try and push it into a higher mode. But let's go back to when we just have this, and let me do an example. But that's exactly right. It's like 2 beams of length L upon 2. If you replace it by L upon 2, you get the 4 at the top. So here's an example. So I brought with me a long ruler. Okay. And so this is 3 feet long. We want this in inches because E is going to be pounds per square inch and I is going to be an inch to the fourth. So it has to be in inches, not feet. This is steel. And the cross section is rectangular. The width is 1 inch. And the thickness is a 1/16 of an inch. Let's see if we can figure out when this is going to buckle. And then maybe I can show you if we get close to that load in practice. So this FC, I'm going to hold this just like I held the ruler, the short ruler, in my hands. And so it's free to rotate at the end. So it's simply supported. So FC, according to the derivation we just did, would be pi squared EI upon L squared. I would have done the plastic ruler, but I had no idea just what that plastic was and what the E was. Here with the steel, I know that E, within a few percent, is 30 times 10 to the 6 PSI. Well, I, in general, is 1/12 B H cubed. If I chose B, the breadth to be 1/16, then H would be 1. Then I would be 1 upon 12 times 16, which is 1 upon 192. On the other hand, if I chose B, the breadth to be 1 inch, and H to be 1/16, then I be 1/12, and now I'd have H cubed, 16 cubed. That's about 3,000. Sorry, 49,000. Let me check that. Yeah, that's 49,000. So this I is a lot smaller than this. That tells you which way it's going to buckle, and that's no surprise. You know, it's like this thing here buckled that way. It didn't buckle this way. Okay. In fact, it won't buckle this way. And so when you do these calculations, you pick the smallest I, because it's going to prefer that direction to buckle. And so that's going to choose, it's going to choose the H, which is smallest, and buckle in that direction, buckle transverse to H. Okay. So it's going to buckle in this direction. So we can calculate this then. That's pi squared. Pi squared is the constant we got. That's Young's modulus. Now we have that's what I got for I. 1 upon that, so it's down the bottom. And then I have L squared. It turned out to be about 4.7 pounds force. So it doesn't take too much to buckle this. Let's see if that works. I'll get rid of this in a second, but okay. Now I'm going to put this ruler on top of this thing, and I'm going to push till I buckle it, and hopefully we'll see what force that takes. That's about 4-5 pounds there, but it starts to buckle at 2, really. This thing weighs about 4 ounces, so it's a little bit of weight. It's certainly buckled at 2, okay? I did this at home first, and so the measured buckling load is about 2. That's comparable. It's not exactly the same, certainly not exactly the same, but it's the right order of magnitude. This is a very old ruler, and I don't think I can show you this on this thing here, but maybe I can show it on my desktop easily enough. But it's good. Okay, you can perhaps see that it's not straight. Okay, it's got some kinks in it. I don't know how many years I had this ruler. They're not very big kinks, but they promote buckling. And so that's reality in buckling. Is when you think that what we do is analysis that has to be perfectly straight. Okay? And so the low value here is because it turns out, so this was a factor of 2. By and large, we're not going to load things like rulers in practice, okay? And so you get very light buckling nodes. When you get very light buckling nodes, imperfections can drop them by a factor of 2. You get more realistic mechanical engineering components, they're considerably more squat, okay? And so you don't get as big a factor as this. I had to have something that was light enough I could buckle it in class here easily, okay? And so that's why I picked the ruler. And it's quite sensitive to this. There is a general tendency, though, that the buckling loads we're going to predict are a little on the low side. And so there's been some adjustments for that. Okay? But we're not going to build things in end load rulers to take any sort of load whatsoever. So this sort of factor of 2 is not right, more like 10%. There was another thing that happened there. If you look at the stresses in this book ruler, let's say we took a 4-pound Then the stress, the compressive stress, or pressure if you like, but if I say it's compressive stress, I'm not going to bother putting a minus sign on. Four times 16, 64 PSI. So if it didn't buckle, 4 pounds does nothing. Let me put, I measured 4 pounds at home, and I got the following deflection. I got a deflection of 3 inches. So now, get a bending stress, M over S. M is F delta. That's the maximum moment in the middle. Okay, there's no moment on the end. S is 6 B H squared. Let's see what that comes to. $18 KSI. Okay, 18,000 PSI, if you like. This is a piece of steel, and I don't know what steel it is. Probably got a yield strength of about 30 KSI. So this is below yield. Let's make it the light. And so if I don't put too much force on it, and I don't yield this structure, but the stresses are considerably bigger, order of magnitude bigger. I don't particularly want to do this, but if I pushed on this hammer, I would get the thing to yield in the middle, and then I'd have a permanent kink there. I could perhaps straighten it out too, but it wouldn't take too much to make this thing yield. So this is a key concern about buckled structures. Let me do a different situation. We can expect that these buckling loads are going to depend on what you do on the ends. If you let them rotate on both ends, then that'll promote buckling, that'll help buckling. If we clamp them at both ends, that would inhibit buckling. Well, why don't we just clamp it at one end and see what wins?
What's the S at the bottom?
Sorry?
What is the S at the bottom?
The S there?
Down. One. Up, up.
S is the section modulus. Sorry. So that's I. And when you go get your bending stresses, when you make Y as big as possible, that'll be Y equals H upon 2. So this will become the 12th goes up top, divide by 2, you get 6. One of the H cancels, you get BH squared. So this thing here is called S, the section modulus, okay, in bending. It's just I divide in half of the height. Okay? And anytime you're doing stresses and bending, the bending stress is always M over S. Okay. So let me treat a different situation. there's no difference to the load whether the thing we're compressing is a beam or a column, okay? It's just an orientation, vertical compared to horizontal. We'll get the same value. Now here's the problem we're going to look at. And if I do something like this, if I build it in, so I'm holding it here, okay, and so it can't rotate at the end there. It'll go like this. It could go, I may be providing a slight lateral load there, but I'm trying primarily to provide a vertical load with the fingers. So it bends like that. And it's perhaps not obvious whether this is going to be easier to buckle or harder. This support stops rotation, but I have no support on this end. So when I did simply support it, I stopped this end moving. I let both ends rotate. So it's not completely clear. So, well, let me take a height X and do this free body diagram in the deformed position. It's not all the way up. So here is the beam. There'll be a reaction F, which will be equal and opposite to the applied load F. But at this end here, to stop this thing rotating, there'll be a moment. And in general, when I'm at height X, not at the top, but there'll be some bending moment here too. So if I take moments about here, I'll get M is equal to the moments in the opposite direction, which is M naught. This moment here is equal to the sum of the moments this way, that's 1. On the other hand, F times delta X doesn't oppose M, so it's minus F delta. Not quite clear what M naught is. Well, we can get M naught by going to the very top of this, and we get the following situation. I go all the way to the top. When I'm at the very top, there's no moment there. This is height L, no longer X, L. And let's call this deflection delta max. That's the biggest deflection. So I take moments about here, M naught is equal to F delta max. So then M and I can do my deflection analysis. And then I'll get to the following. If I substitute this F, it'll have a minus F delta term. I'm going to put that back on the other side. So this is my differential equation. That's for x between 0 and L. And my end conditions are it's built in at this end. So there's no slope there or deflection. Well, I can solve this. It's like this differential equation. General solution. This is just what I had before. I had 0 before. So delta this is like omega squared. So I take the square root. Plus b cos f upon ei. Now this is not 0 here. So in your calculus class, to solve for this, you have a thing called a particular integral, which produces this particular psi. And the way to do this here, this is just a constant. So I'll just take c, a further constant. And when I substitute this in here, I differentiate these twice and add them to this, that'll cancel, but that'll be 0. But the c, I differentiate twice, can be nothing, but the c will go in here. So c equals delta max. Now let me put the slope equal to 0 at x equals 0. Okay. If I differentiate c, there's nothing. If I differentiate the cosine, I get sine, and when x equals 0, that'll be fine. If I differentiate the sine, I get cosine, and when x equals 0, that would give me a. So my solution so far then looks like well, I've got to do this condition here. And so in order to make delta equal 0 when x equals 0, b will have to be minus delta max. So my deflected shape then looks like well, I don't know what delta max is, but what I do know is that at x equals L, I'll have delta max. Delta will be delta max. For this to be true, this must be 0. Well, there are a range of values for that to be 0. The first one is when it's pi upon 2. Next one's 3 pi upon 2. Next one's 5 pi upon 2. This is going to happen. We're going to get to pi when f is increasing. F is going to get to this before this. So this is the first mode. The lowest value that gets you satisfaction of bucking. So that's the case. then solving this equal to pi upon 2, I'm going to get f on EI. I squared that. It's pi squared upon 2 squared is 4 L squared, or FC so lambda is pi squared upon 4. So actually, the buckling load has gone down. And it is easier to buckle. It's easier because it can move laterally. In fact, it looks a bit like this. Here's a zero slope. It's almost as if I had a simply supported beam of length 2L. Okay. And if I had a simply supported beam of length 2L, I'd have pi squared upon 2L squared, and I'd get this. So this half of the built-in or cantilever beam is like half of a simply supported beam of twice the length. Well, there's some other end conditions, and so we'll. Are there any questions on that? These are theoretical critical loads, and they work reasonably well for the sort of beams we do in engineering. Okay, not the ruler so much. And they can all be expressed with this general critical load. In which case FC LE here is the effective length. So when we did simply supported, LE was equal to L. Okay, so that's the standard. On the other hand, when we did this built in, LE equal to 2L. So it's longer. The effective length is longer, like I showed you. So it's easier. If we do a combination of these two, we simply support one end and build in the other end, then you would expect this to be harder to buckle than this. And if that's the case, L goes down, and in fact it does. So it's harder. And the hardest standard situation is if you build in both ends. In which case, shorter still. So what this teaches you is your end conditions matter. And this is the worst situation when you don't have an end condition on one end. Okay. Well, I guess if you made this simply supported, it would just fall over, the buckling load would be zero. But then if you clamp this at the end, there will be a buckling load. This is, so putting them on both ends makes it the standard version, and it is harder than just one end. As you tighten these conditions here, then the LE gets reduced, and so the buckling node goes up. Okay. When it gets reduced by √2, that's half. So the buckling node's gone up by a factor of 2. When it gets reduced by a factor of 2, it's gone up by a factor of 4. Well, let me get start anyway, talking about short columns. There was a question about this earlier. When you get short columns, you start to yield. They have two competing mechanisms, whether they're going to buckle or yield. Pretty soon we're going to start talking about failure theories. When you start yielding things, if you just yield them once and it never happens again, and you don't have large plastic deformation, it's not really necessarily that big a deal. But when you do it repeatedly, you get fatigue, and that is the #1 problem in Meki. So you want to stay away from yielding. So it's reasonable to regard yielding as a type of failure. And so when they get short, these columns or beams, if they're horizontal, may start to yield, and if you cyclically yield them, then they fatigue from that. So it becomes the dominant failure mode. When you buckle them, you can get these big stresses again, and so you can start yielding them too. Okay. So in order to decide what happens when we want a dimensionless length ratio, if you talked about people, you'd say somebody was squat. If what? Well, if perhaps their waist divided by their height started to get to be a significant fraction. Okay. Certainly, if somebody's waist measurement equaled their height, you'd call them squat. On the other hand, if their waist measurement was 1% of their height, you would say they're very, very slim. So we want some sort of ratio like that. Okay. And we're going to use this to decide which failure mode. Liver failure in inverted commas. I mean, as I've said, things can buckle and then go back again and not fail. On the other hand, once they start to do that, they're going to start to see big stresses. And if it happens repeatedly, it probably does lead to fail. And likewise, they may not buckle at all, but they may start to yield. And they see that repeatedly, they will fail. So when we say fail here, we're meaning in the long term. Okay. But a precursor, when you design, if you see this happening once and you think you're going to have repeated loading, then you want to avoid this, even though one-time loading wouldn't really lead to a failure. Well, here's what we're going to do. Here's the critical sketch for buckling. going to be this critical buckling node divided by the cross-sectional area. And we know in general, we can get this buckling node as pi squared EI. A is down here times LE squared. Now, if we write I, this can be done for any cross section, as the area times rho squared. And this form for I, rho, is called the radius of gyration. For example, for a circle, in terms of R, I is pi r to the fourth upon 4. You might be more used to seeing that in D. So that would be 2 to the fourth 16. This would be pi d to the fourth upon 64. In terms of R, it's pi r to the fourth upon. And so that's pi r squared times r squared upon 4. That's A rho squared. So this radius of gyration, rho squared equals r squared upon 4, is r upon 2. So we can identify this. And if we use this critical stress will look like this. I substitute for I as A rho squared. Now the area cancels. So in terms of buckling, this dimensionless ratio is the equivalent length, which reflects the end conditions. Okay? It would be, and simply supported would just straight be the length, but then it's going to change depending on how much you restrain or otherwise the end. And rho would be this radius of gyration. So this is the dimensionless ratio. It's called the slenderness ratio. When it's large, the beam or column is slender. When it's small, the beam or column is squat. And we'll discuss this a bit more, but what we're going to look, so what we have in practice is something that looks like this. The sigma C looks like 1 upon, if you call this x, it'd be like 1 upon x squared. That's a line like this. Okay. We're going to call that SC for buckling. As it gets shorter and shorter, there's also SY for yielding. So if you do experiments, if you get way out here and it gets very, very slender, it's a bit like the ruler, then the things tend to buckle below this. But if you're not too short, then the data is pretty good. On the other hand, what you did in your materials lab, you probably got some points around here. There is a bit of a transition region. So in here we have yielding. Here we have buckling. Here we might have a bit of yielding, a bit of buckling. This is a transition region. And the data doesn't follow this line or this line. I showed you with the rule of some of this data out here is really low. It tends to be a little bit low, and there's some adjustments for that there. I can show you some of those. And you need to have a transition region. When we start to design these columns, then we need to beat this, we need to beat this. So if we calculate our slenderness ratio, we can tell where we are on here and figure out how to do the design. Okay. And we'll have some problems that do that. All right, are there any questions on that?
Yeah, if you had a square beam,
Yes.
could you do something similar to?
Oh, yes. You can,
Like
you
in
can
fluids where you use hydraulic diameter, like
yeah, you can get, that's right.
exactly
You can get a
radius.
radius of gyration for a square beam. So you know, a square beam, let's say B equals H. And the area is B squared. So rho equals B, the square root of 12 to root 3. Okay. So yeah, that's what you would use for a square. And if you had a rectangular one, then you do the half BH and you get a similar result. Okay.
Okay.
So you can always get this radius of gyration. Go look up the second moment of the area. You divide by the area and take the square root. You get the radius of gyration. Then, depending on the end conditions, you can get this length. Okay, and so you can always get this. Okay, for any shape.
Is that B over 2 over 3?
Sorry.
Is that go down your last line? Yeah.
No, B over 2 root 3. The square root of 12 is 2 root 3. It's 4 times 3, and I take the square root of that, I get 2 root 3. About 3.4. Okay. So, and we'll do that in problem set 5, which I'll post later today, along with the solution to problem set 4. We'll start considering this. So that question I got on, yes, this is real. In fact, you get squat beams, you're back in here. You get slender beams, you're out here. Really slender, and I wouldn't worry about that very much. We don't load 3-foot rulers with any sort of load. And so this is fairly good out here. Then there's some sort of transition, and we'll fit this with a curve that fits the data. And what the sort of typical design thing, though, quite often when you're doing the design, you don't know which region you're in, so you have to make a guess. Okay, once you've got some experience, the guesses are usually pretty good. But if you make the wrong guess, it's no big deal. You just discover that and you redo the analysis and assume you're in the other region. There are 3 regions, 1, 2, 3, and it's possible not to get the right region initially when you're doing the analysis. Okay, and you have to try more than one to get it. But that's pretty standard in design. Any other questions? Well, pretty shortly, we're going to go and hook up with a guy, a practicing engineer called Brent St. Blanc, and we'll be doing this on Mohammed's Zoom, but you don't need to log in for this at all. Okay, we're just going to be trying to set up his PowerPoint presentation, and so I'll log out now, but then we'll be logging back in. But I mean, if you want to watch, that's fine, but we're just going to be trying to get his system going well. All right, have a good day.